This talk is going to be about the mobile industry, the mobile network part of the mobile industry specifically, and where we are today and the coming 10 years. A little bit of an outlook, but also taking stock of where we are. But it will also be about some of the challenges that we are facing, and I think they can be addressed by this distinguished ISSCC community for sure. So it's a little bit of a call out to all of you as well, because this part of the industry, the mobile network industry, it has a tremendous opportunity when it comes to how we use networks, but it also has some pretty daunting requirements on us when it comes to energy efficiency, when it comes to even more bridging the distance between the devices, the sensors, and of course, the cloud servers. And that's really what the industry is about, bridging distance, reducing latency, making sure that we do it energy efficient, and of course, keeping up with the data demands from all the applications and the users. Let me just check here, a show of hands. How many are in the mobile network or wireless areas? Can we see some hands here? It's 10%, maybe 20%, something like that. So for all of you, some of this will not be entirely new, but I will talk also about what we need for the coming 10 years, and there, of course, much more of the research challenges. And to the point of the title of this talk, what we see now as we build the network platform, we build the digital infrastructure in between devices and applications, we really fuel not just the innovation, but the demand for compute also on those two sides, on the device, on the cloud side. So a few numbers about Ericsson, key figures. I would say this is to a large extent representative for the whole mobile network industry, but I'll take Ericsson as an example here. So 75 billion gates. That's really what a connection from basically the interconnect point, the core, the RAN, into over-the-air interface, into the device chipset. That's really what the connectivity path touches, 75 billion gates today in early 5G. And a big part, a large majority of that is on the network infrastructure side. Then of course there is some 10-15% on the device side, but this is really about network processing needs. And it's just going up, as I will show you. And then when it comes to node technology, yes, we are of course on the leading edge when it comes to 7 nanometers, 5 nanometers moving to 3 nanometers in FinFET and surround gate, or gate surround. But what we are also realizing is that this is not the only way for us to scale. And Lisa was into it this morning. This is much more about architectural principles for us, but it's also very much about the relatively low scale that we have in terms of chips that we put into the infrastructure. If you compare to the device industry, the laptops, or even the server industry, of course, we are at a much smaller scale. So we have to be smarter about how we build these systems architecturally, as well as leveraging heterogeneous architectures. The 120 decibels, that's dynamic range. And if you think about the difference between that faint signal from the remote sensor compared to that watt transmitter just next to you, that 120 dB dynamic range is really needed. And that puts some extra requirements on us on the A to D DJ, but also the signal processing compensation for imperfections in the chain. In fact, this is an area where we have to have very dynamic precision, so 24 bits at some points, and of course much less in others. And the more than 10 gigasamples per second, that's really because we want to combine a number of bands, do processing over basically everything up to 5 gigahertz in one go, or if we're talking about higher frequencies like 28, 39 gigahertz, of course, we want to have a bandwidth of roughly 2 gigahertz. And of course, that requires these kind of sample rates, and it's going up very quickly, actually. And it was well covered in an earlier talk here as well, why this is a critical part of the system. From an Ericsson point of view, we are delivering 5G networks now all around the world. Actually, around 140 of those networks are live with Ericsson gear, and that really shows how critically important it is to have your own development of silicon ASICs as a part of this offering, because that gives better energy efficiency, that gives better performance in terms of uplink, that gives better performance in terms of capturing all this data growth that come from 5G devices. And it fits into a network infrastructure, of course. Starting on the radio side, I already mentioned that this is where we talk about the high bandwidth and the needs from not just the PAs and the ADDA, but actually the front-end compensation. That is consuming a lot of those gates, actually moving all the processing from central baseband into radios. That means that the radios need advanced ASICs, and then I will come back to that in a moment. Is of course the baseband processing, where it's much more about shared resources and using that compute cluster to process hundreds, if not thousands, of sessions at the same time. And transport, that goes without saying, is a big consumer of advanced technology as well. And all of this is really, of course, connected to advanced network functions, software, AI-driven more and more, that makes best use of the hardware. And if you think of it, this combination of a very dedicated hardware that is energy efficient, but also really tailored to the needs of every device, combined with advanced AI and automation software, it becomes a very complicated, very advanced distributed system that needs to be managed in lockstep between the hardware and software. And that's, of course, also one of the reasons that we have to continue to push the boundaries when it comes to our own ASICs, when it comes to hardware that solves this integrated with the software. Now, some of us have been in the industry for a very long time. If you look back at the 30 years that has passed, from 1990, where we basically started with digital mobile systems, digital communication. And it was about voice call, of course, and text messages. And every 10 years, we have increased the data rates by around factor of 100. So we have now achieved 1 million times higher data speeds in wide area networks, in mobile systems, compared to 1990. So from around 5 to 10 kilobit per second to similarly 5 to 10 gigabit per second today. And that is, of course, a very fast pace in terms of technology development and innovation. And as we heard from Lisa earlier today, this, of course, beats roughly 2 times every 2 years. But on the other hand, we were helped by increasing also the spectrum. So we're using more and more spectrum. But even so, this is an important data point. So we are moving at a very rapid pace when it comes to not only handling the peak rates, as this number shows, reducing the latency, reducing the energy consumption, overall bringing an even more efficient communication system. And that, of course, is really the starting point for where we are today. When 5G now is not only used by smartphones, how many 5G smartphone subscriptions do we have now, end of 2022? About 1 billion 5G subscriptions have already been rolled out. And in the coming 5 years, we will see another 4 billion. So 5 billion 5G subscriptions in just 5 years' time. So it's really moving at a very fast pace. But that also means that the smartphones is just one part of the 5G ecosystem. The rest is really the connected devices, the sensors, smart enterprise connectivity that goes beyond just your local connectivity. It really becomes part of that distributed infrastructure. And when it does, of course, it changes the way we do work, not just in wide area systems like the fire truck or the ambulance here, using network slice technology to have the right quality of service for that session, the right security, the right latency, and so forth, the right bandwidth. But it changes every other industry sector as well, because you can build on, you can leverage this phenomenal technology that has global reach, but also have the performance and the cost advantage of this system. And this is really where we are today. Going into the enterprise space, you see examples from, as I said, transportation, where basically all public safety now is moving to 5G. You see that in rail, you see that in utilities, you see that also in smart factories, for example. So our own factory, where we're building 5G, there, by using this wireless technology from day one, when you build a greenfield factory, you can reduce energy by 25%, you can reduce water waste by 75%, you can get double the productivity per employee by using this technology in AGVs, in inspections, in your AR glasses, but of course also in the regular connectivity on site. And that's just showing that this is going to happen over the coming 5 to 10 years, a massive transition into using the network more as a platform, more as a service for every enterprise, for small, medium businesses all the way to the large enterprises. And that's a good thing, of course, because the industry needs this scale to be able to continue the innovation. The industry also needs to reach out, because now we are changing how you're building things, not just in the communication and connectivity space. You're changing things in terms of automation and processes all across the digital stack. And that's really where partnerships comes in. It doesn't work to do it all alone. It really requires all of us to work together. So what's next? What's going to happen over the coming 10 years? Well, I see that we have a chance, and we do have to work hard on it, but we do have a chance to continue this trajectory of 100 times higher performance in the coming 10 years. It's going to be a challenge, that's for sure. It's not going to be perhaps as easy as the previous 30 years, but it is certainly doable. And it's a combination of really advanced signal processing, really advanced antenna systems, but also, of course, some more spectrum to go with that. And the higher up we go in spectrum, the more complicated it becomes for the compute part as well. And that's something that we need to sort of battle with at the same time. The 4 areas that we believe are most important when it comes to 6G is really to look at this unlimited connectivity or communication, which means that we need to get indoor, we need to get to satellite, we need to get to wide area beyond today's terrestrial systems. But it also means, as I've said before, energy efficiency. We have to break the energy curve. We have to basically stay at the energy consumption that we have today, despite the continuous exponential growth of traffic in the networks. We have to bring the compute into the networks much more than today's edge compute, which is really only at the edge, so to say. We need to bring the compute part even further out in the radio network. And certainly we need to build trust in this infrastructure by security. Hardware security was mentioned already before, and Ingrid got well-deserved recognition for that. This is absolutely critical, to build in hardware security from day one when we go towards 5G Advanced and 6G. And then the last part is, of course, the automation. Automation and AI is already paving its way into the digital infrastructure. We are really touching the surface of that, or scratching the surface of that, with AI-driven automation for how to run networks. But over the coming 5 to 10 years, we will build AI capabilities at all layers, including at the lowest level of the base station. There, of course, the inference will require less precision. A few bits of precision would be enough there, but this whole scale, this range of capabilities that then will permeate in the digital infrastructure, including the radio network, will be a key driver for 6G. In fact, we will combine this unlimited connectivity of the wireless part with the cognitive network, or the AI part, that already is starting to happen. So those 2 pieces will have to advance at the same time when we go into 6G. 2 other very important areas, and this shouldn't come as a surprise, but we are connecting sensors today, but those sensors still need to be charged. They still need a battery. They still need to operate with some kind of maintenance. And when we look at 6G, this is really where we see the opportunity to completely remove the batteries or make them energy harvesting. And one good example of that is the work that we're doing together with MIT here, where we are showing that in a 6G context, we can actually, through the same framework, what 6G will cover, we can start to capture the opportunities that comes from energy harvesting sensors. And that's partly possible already today, but not on a wide area scale. So over the coming 5 to 10 years, I think we'll see the development that will allow that to be full-fledged citizens on the 6G network with security. Of course, many other constraints will have to be there, but still it's a part of that 6G vision that we're working on right now. The other part, which is also to some extent connected to the energy efficiency that I mentioned, but it's also connected to this unlimited connectivity. We need to get really good performance everywhere. And what that means is indoor systems, as I mentioned, is to go beyond today's terrestrial macro systems into even satellite systems. And of course, that gives new requirements also on the compute as well as the signal processing part. This is where latency, coming down to sub-milliseconds and closing this divide between the physical and the digital world in the cyber-physical continuum, will have to come together. Today, we are expecting the lightweight AR glasses in just a few years' time to be more readily available. But when we go towards 2030, we see that we need to provide much more support from the network side, basically running all or a large majority of all the compute on the network side. creating that immersive experience. So that's a little bit about the journey. We have had this fantastic run for 30 years. We are continuing on the same path over the coming 10 years. The innovation continues towards 6G. But as I said, it doesn't come without really turning every stone to get to another 100 times in the coming 10 years. I mentioned a little bit about data. So how much is data growing in today's network? Well, it's actually continuing to skyrocket. And today, a large part of that is video, of course, downlink heavy. This is really where you have 70% or so in most networks are video, downlink heavy. And you can see on the left-hand graph here that, and this is a prediction out until 2028, so the coming 5 years. You can see the yellow part here is showing the traditional or now legacy mobile data systems from 4G, 3G, 2G, tapering off and basically going down in the outer years. You see the growing part of 5G mobile data, really growing to be the majority already in we could say 3 years. Around 3 years, you would start to see that it is coming to be at the same level or even increasing. And then you see the purple even being more than the legacy system. And then you see the purple part here. And what is that? Well, as I mentioned, if you have this scalable technology that works all around the world, and it works both outdoor, indoor, when you have mid-band or roughly 3.5 gigahertz spectrum to use for 5G. You're not only using the rebanded low bands, you're not only using the high bands around 20 to 30 gigahertz, you're using these mid-bands between 3 and 4 or 3 and 6 gigahertz. Then you get this fantastic capacity that allows you not only to get good smartphone experience, but is good enough for fixed wireless access. So you can actually start to replace the residential access or the, as I mentioned before, the small, medium businesses access with wireless technology. Getting that flexibility so that you don't have to dig fiber to every endpoint, to every home, but you can actually start to leverage the technology at a cost-efficient manner to serve also really demanding, high-demand customers that have SLAs that needs to be honored, but also that start to tap into the enterprise usage. So remote worker over the last 2 to 3 years is a norm, and I think we will be able to serve that usage pattern over the coming years through fixed wireless access. And as you can see here, in the outer year, it's a very substantial part of the network. And for those of you in wireless and in network dimensioning, you know very well that once you start to get to fixed devices, fixed endpoints, the whole dimensioning changes. That's really where you need to start to have super advanced beamforming. You need to be very smart about the scheduling, but you also need to look at the patterns, the usage pattern of these fixed points, very, very different from the mobile that roam around. So for the whole industry, making sure to cover both the use cases of full mobility, wide area mobility, as well as local or directed connectivity, directed access to fixed points or fixed places, that's going to be really critical in the outer year here. But again, some of us already enjoy these services. This is becoming technically, commercially feasible, and is really skyrocketing on that part. The right-hand side, it really shows how this will evolve around the world. So coverage by existing technologies, 4G, 3G, 2G, is already at the 95% population coverage worldwide. Doesn't mean that everyone is using it. As you all know, we have a digital divide that we need to close. That's more on the device and the literacy side. But when it comes to having coverage, is around 95% population coverage around the world. But then you see the orange curve here, where very rapidly 5G coverage will be built out, basically offering this connectivity layer that serves them both consumers and enterprises, reaching more than 80-85% in the outer years. It's only 5 years from now. So that's a little bit about the industry, where we are in the coming 5 to 10 years. Is 5G then a driver for compute need, or is it enough with standard CPUs? Is it enough with the capability that we can basically buy off the shelf? Well, I think Lisa was into it very much this morning. It's certainly not enough for 5G today, and if you look at 5G Advanced and 6G, even more pronounced the needs to have unique ASICs, to have tailor-made and heterogeneous compute capability along the chain. And this is really showing how the trend, or rather the numbers from 2010, roughly, where we introduced previous technology, 4G LTE, to the left until today, 2020, roughly. And you see the different colors here. At the bottom here, it's about radio control and packet processing functions and layer 2 processing, while the green, orange, and black one is layer 1 beamforming and digital front-end processing. So going back 10 years, we used to have a 20 megahertz carrier. We used to have maybe 2 transmit and 2 receive antennas, and we were talking about doing all the processing in a millisecond. Fast forward to where we are today. Now we're talking about 100 megahertz carriers, at least, and I mentioned carrier aggregation before. We're talking about 64 transmit and 64 receive for a macro system, and we're talking about doing that processing 160 times more processing in half the time. So of course, this cannot be done cost or energy efficient without having unique hardware. And this is really where the Ericsson silicon comes in, and this is where the whole industry is now investing in making sure that we can cover this compute need in the most efficient way. And it's actually just continuing in this way. And the reasons are obvious. One is to keep up with the data, but also, as I mentioned, we are talking about multi-band systems. We are using wider bandwidth PAs and wider bandwidth systems to be able to carry aggregate between a number of low bands, but we also have more bands coming up in the mid and high band range. And of course, that requires wider bandwidth and therefore even more than the 100 megahertz indicated here. So is this good news? Well, I think it is good news in many ways, but it's also very challenging because this processing cannot be done remotely. This processing needs to be done distributed and very, very air interface near. And that, of course, put extra requirements that it cannot be shared. This is compute that is more or less dedicated in the radios, in the antennas, all the way out on the site. But at the same time, this is really the way to drive energy efficiency, drive higher uplink performance. I mentioned before that one of the key requirements now when we move away from consumers and the downlink heavy traffic patterns into more uplink balanced scenarios with XR, with immersive experience, where you are moving some of the workloads from the smartphone, from the glasses into the network edge, then of course the uplink becomes so much more important. And to be able to do good uplink performance, you need to do the processing very air interface there. You need to do all of this processing in the radio. It cannot be done centrally, it cannot be done on the baseband. So it is a necessary step, but also a very, I think, important step in order to keep up with the demands here. And this is really why this comes together in a unique family we call Ericsson Silicon that handles a range of ASICs from very, very radio near all the way to baseband and centrally. So for those of you who are perhaps less into mobile macro infrastructure, why do we need to go down this path? Why don't we just have smaller cells? Why don't we just densify the network and get rid of some of these challenges? Well, first of all, it doesn't really scale. We need coverage in the system to bring down the cost of the infrastructure. That's still true. And that coverage needs to be as big as possible, which of course means advanced beamforming for the mid and high bands. But that coverage then requires us to handle the very sort of big dynamic range, 120 dB, as I mentioned. To be able to listen to that faint cell edge device, the sensor, and at the same time being able to block out that watt transmitter next to you or on the same site. That really requires the latest hardware on that side. Users, of course, if you have large cells, you have many users in the cell. That in itself is a demand, and these users have higher and higher demands on the network. Absolutely clear when it comes to new users pattern, XR being the obvious example now, which drives in itself the need for higher bit rate, and those bit rates, of course, means that we are using more of the spectrum. We need dynamic spectrum sharing, we need advanced usage of both the mid-band, the low band, and the high band. And that spectrum that needs to connect it is not enough today. We need to continue to drive towards higher bands, and when we go to higher bands, Of course, signal performance or the performance in general means that we need to compensate even more on the silicon side. And that in itself, coming back to the coverage, need big coverage sites, becomes a virtuous circle here. For every generation, for every step we're taking here, it just continues in this way. And then, what about the other parts here? If this is the network evolution, there we are talking about the drivers for the network to involve or to improve. Combining that with the development on the device side, of course, we already see much of that in the XR space with AR and VR glasses, but even more so in the connected enterprises, the advanced automated drone deliveries, all the things that will be wide area autonomous systems. And then combining that with the full application suite, being able to really do everything over that one network. It becomes the same needs that we now need to fulfill on the network side. Higher performance, lower latency, higher energy efficiency. Those very same needs then are prevalent, of course, on the cloud and device side as well. But it doesn't come without thinking about this end-to-end. So while we previously, and certainly during the 4G era, took for granted that we can handle the connectivity at the right cost, at the right price, just connecting a device ecosystem and connecting a cloud ecosystem, now we're talking much more about opening up the networks, being able to run it in some parts on-premise, in other cases for macro systems, making it open and programmable. Of course, that's a big change in the industry as such. Puts new requirements both on the hardware and the software, but also the openness towards partners in this space. And while we today see great momentum around the smartphones and the early enterprises, this is a journey that cannot be done alone. This really has to be done cooperatively across industries. And I think this is really where the coming 10 years will show whether we are on the right track or not. Can we work together across hardware, software, automation? Can we work across industry and sectors? Because now we are moving this 5G Advanced and 6G infrastructure to be fundamental for societal functions, meaning we're going to critical infrastructure, we're going to cases which are much, much higher in demand than today's system. And we do think that we can do that, but only by working together. So then, finally, what does this take in terms of hardware? What does this take in terms of what we can do here, what the community here really needs to do? Well, first of all, it's very much about looking at the requirements, specific requirements for mobile infrastructure, which are different. The distributed infrastructure, as Lisa was into in the morning here, will put higher requirement on tailor-made systems. But it's also about enhanced network performance. It's about this uplink performance enhancements. It's about dynamic spectrum sharing, all of these things that needs to be done very radio near. And as I already mentioned, we are breaking the energy curve, meaning that from now on, we can no longer, for introducing new technology in the network, we cannot increase the total energy consumption. In fact, with 5G, with the kind of deep sleep or the lean carrier concept, we are already breaking the energy curve, so we are not increasing the energy despite the traffic growing with more than 40% per year. But going forward, of course, we need to get that curve down, and of course, over time, we'll get it to zero with a total commitment on CO2. But as we do this, we are building new capabilities into the distributed infrastructure. And part of that is really the security, the hardware security at the core of this, at the core of every chip, but also at the core of the digital infrastructure. We have the capabilities now, and this is what we build in from scratch to have hardware security, but we also have a need from these other industries, the enterprise side, to be able to secure infrastructure from hardware, software, and of course the AI and automation on top. So, what is the takeaway then for this group or for this community? I would say that if we look at the coming 10 years, we have the challenge, but also the opportunity to continue on the path of 100 times more every 10 years. Latency will be important. Energy efficiency will be super important. But we also have the opportunity to expand and use this capability across these other sectors, whether it's in the sensors, whether it's in the sensing part of the infrastructure, or whether it's in terms of the applications that can be network aware and therefore optimized together with the network. This opportunity, I think, is in front of us now. Think of it in a similar way as a smartphone journey over the last 10, perhaps 15 years. The cloud transition, the app economy, all of those things are now available as base capabilities to the society, to small, medium businesses, to enterprises. And as such, of course, it will drive even more need on the network. But that can be done, I believe, by looking at the opportunities of innovation also on the network side, similar to how we looked at it on the cloud side and on the device side. And that actually means that I'm going to end here, and hopefully we have created some more interest in the innovation in the network infrastructure part as such. This chip is, this is where we on the baseband side are more than 40 billion gates. If you look at the radio near side, we are at 13 plus billion gates. So of course, there's a lot of capability that needs to go into today's and of course next generation systems. So with that, thank you.